Hello and welcome to Structural Integrity's Material Science Center. Today I want to talk a little bit about the process that we go through when we're doing failure analysis of parts and components that our clients send in. The first thing that happens is samples arrive at shipping and receiving and get logged into our computer system, which we use to track projects from start to finish. In the shop we also have a tracking system on the board, so at any point in time we can very easily see where we are with regard to the overall investigation. For larger samples or components, we often want to cut those down to a more manageable size so that we can examine and analyze features of interest like fracture surfaces, areas where there's corrosion on the sample, or other features of interest. We do that with the larger marble saws, and at some point we often have to use the smaller saws that you see in the background over here to cut down samples to be examined in a microscope or for mounting for metallographic examination, which I'll talk about in a moment. One of the early steps of the failure analysis process involves documenting samples in the as-received condition. For larger components or samples, we normally do that in the shop where we have a lot more space. But after samples have been cut down, or in the case where we receive smaller samples initially, we can take pictures here in the photography room. Normally what we're doing here is trying to document features of interest, which might include fracture areas, areas on the samples where there's corrosion, mechanical damage, wear, or features of interest that might indicate something that's associated with the cause of failure. Once we have samples cut down to a small size in order to do metallographic examination, we either mount the sample in a media such as bakelite using the presses in the background here, so that we can do polishing and etching more easily. Or for some samples, like a ring section or some weld cross sections, we can actually polish and etch the sample without first mounting it. So we go through a process of grinding, starting with very coarse sandpaper and going to a fine sandpaper on the polishing wheels here. The final polishing steps are done on this side, and with these machines we take the surface finish down to a mirror finish, so that when we etch the samples using an appropriate acid, it brings out the microstructure, including grain size, fracture or crack morphology, inclusions, or other things in the sample that we might need to see. And all of this information feeds into the overall failure analysis process. For many of failure analysis projects that we do, it's real important to do fractography and examinations using the scanning electron microscope. The SEM is capable of doing documenting fracture surface features up to about 4,000 or 5,000x, and it produces a really nice depth of field, so you get clear images even at high magnifications. In particular, it's indisposable for failure analysis in that it's very helpful in identifying the failure mode. Within the SEM is a detector for energy dispersive spectroscopy, and otherwise known as EDS. And EDS is very useful for corrosion failures because EDS helps identify the elements that are present in the corrosion product, and from that information we can quite often figure out what the substance is that's causing corrosion on the metal surface. Once our metallographic samples have been polished and etched, we can look at the microstructure or features of interest using the metallographic microscopes here in the microscope room. Typically we're looking at crack morphology or surface conditions. In some instances we're looking at weld microstructure and features associated with the welding process. In some samples we're looking at grain size or inclusion content. And basically we're just trying to get information metallographically that helps figure out what caused the failure. In the microscope room we also have a couple of stereo microscopes. These are very useful for looking at three-dimensional features, corrosion pits or fracture origin areas. We don't do a lot of documentation with this instrument, but it's great for doing visual examinations. We also have a digital Keonce microscope, which is similar to the scanning electron microscope in many ways. It doesn't work in a vacuum chamber, so we can look at larger samples, but it produces a real nice depth of field. It also produces color images up to about 2,000x magnification. This does not do the energy dispersive spectroscopy, which has to be done in a vacuum chamber. But overall, this is a very useful instrument for failure analysis work. Hardness testing is a very simple but effective tool in failure analysis. We have in the hardness testing room, we have a benchtop Rockwell hardness tester, which is great for bulk samples. We also have Vickers micro hardness testing machine, so that if we're doing hardness measurements in a real small cross section, either like a thin wall tube or in an area that's case hardened around the surface of the sample, the Vickers machine is very nice for pinpointing small indentions and taking readings that way. The LECO automated machine is very useful for welds and bigger samples because you can set up a grid pattern, and in the case of a weld sample, you can do a hardness grid that extends from the base metal into the HAZ and weld metal, and it'll kind of provide information that's sort of a map of the hardness profile for an area of the sample as opposed to a single location. Once we've gathered all the information through testing and examinations, the final thing that we need to do is to take all of that information, combine it with the information that we get from the client regarding operating conditions such as temperature, pressure, abnormal conditions, or what have you. We process all of that and make a determination as to the cause of failure. And finally, we put the information into a report with images describing all the testing that was done and the process that we went through to reach those conclusions. And that's the basics of the failure analysis process.